So polyprotic acids are acids that can donate more than one proton in succession. NH4 plus is actually an example of this. It can go ammonium, NH4 plus, right? Let me just write this out so you can see it, because I talked about it in the previous video. NH4 plus, right? And then if you give up a proton, it's an acid to give NH3. That could be a base, but this is actually amphoteric. It can go on to give on another proton and make this amide, okay, anion. So that's an example of a polyprotic acid. More common one that people think about is phosphate. And so we can show that here with the pKa's. And so if you think about H3PO4, that's phosphoric acid. And that is basically capable of giving up a proton and making hydronium and this H2PO4 minus anion. So that has a certain pKa around 2. We can call that pKa 1. We can do that further. And this can continue to give up a second proton, make what some people call hydrogen phosphate or biphosphate. Hydrogen phosphate is probably a better word, and this would be called dihydrogen phosphate. This has a pKa of 7.2, and then the hydrogen phosphate anion can continue to give up a proton and just make the phosphate triply deprotonated ion there, and that has a pKa of about 12. And so what you can end up doing is, and I won't go over the calculations here, this is sort of a general chemistry, more complicated general chemistry type calculation, but you can look at the speciation of the various phosphate ions as a function of pH, and you can see these clear patterns here. So I expect that you would be able to know how to rationalize this. And if you were really forced to, probably you could look up in a book and remind yourself how to do these calculations. But let's go over just some of the simpler aspects of it. When your pH is equal to the pKa of something, that means, according to the Henderson-Hasselbalch equation, that you have 50% of the acid and 50% of the conjugate base. So if you look right here, this is where these lines cross here, that's telling you have 50%. So here you have 50% phosphoric acid as a species and 50% hydrogen phosphate. And where is this value? That value is right by 2, a little bit ahead 2. It's at 2.12, right at the pKa 1. The next one right here, this is right at pH 7.2. Okay, and at 7.2, you're going to have 50% hydrogen phosphate and dihydrogen phosphate, I should be calling this, and 50% of the blue species, hydrogen phosphate. And then lastly, at pH of 12.37, you're going to have 50% of hydrogen phosphate and 50% of phosphate. Obviously, if you go to very basic conditions like pH 14, you're going to have mostly phosphate. And again, just building up some intuition for this. Remember, pH and pKa's and all this stuff, it's logarithm scales. So if you go to 1 unit past the pKa 2, so let's say you go to pH 8.21, that's going to be at a point where you have 10 times as much of the deprotonated form as the protonated form. So again, building up that intuition with this logarithm relationship, that's why you have the plots, looking like this, where they're really accelerating and decelerating with pH, because this is a logarithmic scale.